Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest. Find the sum of power of all subsequences. The problem is not that difficult. Rather, the problem understanding the problem statement is a bit tricky. So, if you are if you have solved recursive dynamic programming problems in the past, you should definitely give this problem a try by yourself before moving forward in the video. As always, we will dissect the problem, solve it step by step, and understand the exact thought process behind reaching the final solution. So, with that, let's get started. The problem states that we are given an array nums of length n and a positive integer k. Now, the power of an array is defined as the number of subsequences with their sum equals to k. Now, our task is to figure out the sum of power of all the subsequences of num. And since the answer can be large, we have to return it modulus 10 to the power 9 plus 7, right? So let's take an example. Let's say nums is 2, 3, 3 and k is 5. That is, we need to figure out the sum of power of all the subsequences of 2, 3, 3. So how many subsequences are there for this array? Total 8 subsequences, including the empty one. So this is the first subsequence, this is the second subsequence, this is the third one, fourth one is 2 and 3, fifth one 3 and 3, sixth one is 2 and 3, seventh one is the entire array 2, 3, 3, and the eighth one is the empty array, right? Now for each of these 8 arrays, or for each of these 8 subsequences, you need to figure out the power and sum them up. That will be your answer. So let's start with one subsequence first. So one subsequence, if you remember, the seventh one was 2, 3, 3. So let's start with that only. So we have this subsequence 2, 3, 3, or in other words, we have an array 2, 3, 3. We have to figure out its power. What is power? Power is defined as the number of subsequence with their sum equals to k. Now for this array, notice this was the subsequence of the original array. Now even to figure out the power of this array, you have to figure out how many subsequences of this array are there which has a sum of 5, because k is 5. So in this case, there are two different subsequences. So 2 plus 3, which is equals to 5, and similarly 2 and 3, which is, if you sum them up, it will be 5 as well. So only two subsequences of this array has a sum of 5, and hence the power of this array is 2. Similarly, you will figure out the power of all other subsequences of nums, sum them up, and that will be your answer. So if you do this exercise, you will see the total power of all the subsequences is 4, and hence 4 is the answer. So hope the problem statement is clear. Now how to solve this? Notice there are two parts in the problem. First is figuring out the power of an array. Second is, once you have figured out the power of an array, you have to figure out the power for all the subsequence of the given array nums. So let's focus on the first part first. This is a very standard dynamic programming problem. So if you are new, or if you know the solution for this already, feel free to jump to the next section of the video. If you don't know, just continue watching. So we need to figure out the power of an array. That is, if this is the array and k is 5, we need to figure out how many subsequences of this array are there which has a sum of 5, right? So if you do it in a naive fashion, it will be of the order 2 power n. That is, you will iterate over all the subsequence, see their sum, and see if it is equals to 5 or not. If it is not equals to 5, you will not count it. If it is equals to 5, you will count it. So that solution will be exponential, which surely will not pass. So we have to optimize this. Now notice what you can do with the first element. Either this will be part of your final subsequence, or this will not be a part of your final subsequence, right? So if this is a part of your final subsequence, this will contribute to this sum as well, right? So two choices, either this is a part of your subsequence or not part of subsequence. So let's assume this is not a part of subsequence. So in that case, what you are saying is give me the number of subsequence from this array such that the sum is equals to 5. So isn't this problem exactly equals to the original problem? The original problem was, given this array, tell me how many subsequences are there which has a sum of 5. Now you are saying, given this array, tell me how many subsequences are there which has a sum of 5. So both are exactly same problem, just this second problem is a reduced version because it has less number of elements in the array, right? So this was the scenario when you have not taken this element, but let's say you have taken this element in your subsequence, you decide to take this element. So in that case, what you will say, this is the remaining array, tell me how many subsequences are there such that their sum is equals to 3. Now why 3? Because you already have taken element 0, that is you already have taken 2 in your subsequence, so you want the sum equals to sum of 5. So the remaining elements should sum to 3 for the entire subsequence to sum to 5, right? And hence you will say, from this remaining array, tell me how many subsequences are there which has a sum of 3. Now again, this is also exactly equals to the original problem. It's just that the array is reduced and the value of k is also reduced. So hope you can see the recursion here. From the original problem, we are coming back and solving the same problem on reduced array or reduced constraints. So this is exactly what recursion is. So if you figure out a function, or if you find a function that will take in an array and a sum, and it will give you how many subsequences are there of this array which has a sum of s, right? Now initially you want your entire array here, and initially the s would be 5, that is you want a sum of 5. Now you have two choices here, right? Either you will take the 0th element in your subsequence, or you will not take 0th element in your subsequence. If you don't take 0th element in your subsequence, you need to solve the exact same problem but with reduced array size. Previously this array had 2 1 3 3 2 5. Now this array would have 1 3 3 2 5, right? So basically the same thing but with reduced array size. Similarly, if you take this 0th index, you will solve the exact same problem, that is you have to figure out the sum of number of subsequences such that the sum is equals to 3 now, because you have taken this 0th element and the value of 0th element is 2. So whatever subsequence you will form will have 2 in it. So the entire subsequence sum should be 5. 2 you have already taken. So what should be the sum of the remaining subsequence? 3. So you want a number of subsequence from the remaining array which sums to 3, right? So this is exactly what the recursion would look like. Now notice that if you pass on the entire array every time, you can't memorize it easily, right? That's where instead of like forwarding the entire array, you can simply forward an index. Why? Because at any given point of time you are only dealing with the first element, right? So at any given point of the time, your remaining array would be a suffix of the original array. So initially you will start with f of 0 comma 5, that is you want everything starting from 0th element to be considered, and you want number of subsequence of this entire array which has a sum of 5. Now after you transition, you will say, if I don't take, I want f of 1 of 5, that is starting from first element, that is this particular array, give me number of subsequence that has a sum of 5. And if you take this, you will ask for f of 1 of 3, that is again starting from first element, give me how many subsequences are there which has a sum of 3, right? So hope this recursive state is clear. If this is clear to you and if you know how to memorize this, feel free to move forward to the next section of video. Otherwise we will do a small dry run for those who don't understand this still. So let's do a quick dry run. Let's say we want to figure out how many subsequences are there which has a sum of 5, right? So as we discussed, f of 0 of 5 is what we are looking for. That is, how many subsequences are there which starts from the array which starts from the 0th element, that is this entire array, such that the sum is equals to 5, right? That is what f of 0 comma 5 denotes, and that's what exactly what you want, right? So you want f of 0 comma 5. Now what will happen? You will look at the first element of the array. The first element of the array is 0th element. So either you will take it or you will don't take it. If you don't take it, this is your remaining element, this is your remaining array, and you still want a subsequence such that the sum is equals to 5. So because this is your remaining array, you will say I want f of 1 comma 5, right? But if you decide to take 0th element, then your subsequence that you are forming already have 2, and you want the sum to be 5. So the remaining subsequent sum should be equals to 3. So you want f of 1 comma 3, that is starting from the first element. If I consider this entire array starting from the first element, give me how many subsequences are there which has a sum of 3, and that's what you want as well. Now let's figure out f of 1 comma 5. Again, that f of 1 comma 5 denotes how many subsequences are there for the array starting at 1 such that the sum is equals to 5. Again, you will take the first element of the array, see if what to do with the first element. Either you will take it or you will not take it. If you don't take it, you will be remaining with this array and you still want how many subsequences are there which sums to 5, that is f of 2 comma 5. But if you take it, you will be remaining with a subsequence which should sum up to 4 now. You want subsequence of sum 5, but because you have taken this, you already have one element which has a value of 1. So the remaining sub element that you want should have the sum of 4, right? So f of 2 comma 4 is what you want if you take this element. Now let's figure out f of 2 comma 5. So again, same thing, f of 2 comma 5 nodes starting from index 2, that is this particular array, give me the number of subsequences which has a sum of 5. Again, two things, take the first element, either it will not be a part of the subsequence or it will be part of subsequence. So if it is not a part of subsequence, you need how many subsequences are there starting from element 3, that is sum of 5, that is f of 3 comma 5. But if it is a part of subsequence, you will need, basically you have added one thing to your subsequence, whatever subsequences that was there, you added one more element which is 3. So you wanted the subsequent sum should be equals to 5, you added 3, so the remaining subsequent sum should be equals to 2. So you want number of subsequence starting at index 3 which has sum equals to 2. So in the same fashion you will continue doing. So if you figure out f of 3 comma 5, basically it says that starting from this, give me the number of subsequence that has sum of 5. No matter what you do, you will not be able to make a sum of 5 from just 3. So f of 3 comma 5 is simply 0. Similarly, f of 3 comma 2 would also be 0, because no matter what you do, with just 3 you can't make a sum of 2, right? So what will be the value of f of 2 comma 5? 0 plus 0, which is 0, right? Now in the same fashion, if you figure out the value of f of 2 comma 4, you will want f of 3 comma 4 and f of 3 comma 2. Again, this 2 will be 0, so the value of f of 2 comma 4 will also be 0, which in turn says value of f of 1 comma 5 will also be 0, which means starting at index 1, there are 0 subsequences which sum up to 5, and you can see there is no subsequence at all which will sum up to 5. You have 1 and then 3. So no matter how you make the subsequence, you will not be able to make a sum of exactly 5, and hence this 0 is correct. So in the same fashion, you will continue and you will finally get the value of f of 0 comma 5, which will denote the number of subsequences which is starting of the array which starts from index 0, that is complete array itself, which sum up to 5, which is k. So what like how does the pseudocode look like? Pseudocode for this recursion would simply look like this: f of index comma sum. If sum is less than 0, you will return 0. That is, if you are asked to form a negative sum, no matter what you do, you will not be able to make a negative sum because every element of the array is positive. So you will simply return 0. That is, there is 0 subsequence with this particular sum. If index is n, that is, if you have exhausted all the array, then only thing you can make is 0. You have exhausted all the array, so you can't add any new elements. So if you don't able to add any new elements, you can only make a sum of 0. So if you will see if the sum is equals to 0 or not. If it is 0, it means you are able to now make one subsequence, otherwise you will not be able to make any subsequence and you will return 0. Now these are the two base cases. Now if this doesn't satisfy, you will look up in your table. Now why, we will come to that, but let's move forward. Let's say it is also not, it is also equals to -1. So you will see you have two choices: either you will take this or you will not take this. By this I mean the starting index, which is IND. So if you don't take the index IND, the total sum you want is still sum, and the remaining array is starting at index plus 1. So you want f of index plus 1 comma sum. Otherwise you will take the index IND. So in that case, the remaining array is starting at index plus 1 and the subsequent sum that you want is sum minus array of index, right? So f of index plus 1 comma sum minus array of index is what you want. You will simply sum them both and this will give you how many subsequences are there starting for the array starting at IND with a sum of SUN. Now notice that you may have to compute the same state again and again. So you have computed f of 3 comma 2 here, you might need f of 3 comma 2 again, right? So instead of expanding the tree, so currently it's small but it can be used as well, right? So instead of expanding the tree every time, you can simply store the value for every state in a 2D array, and if you have the value already, you will simply return it from the 2D array. Otherwise you will compute and store it in the 2D array itself, so that next time when someone asks you to compute the same thing, you already have the value in the array and you will return it directly without doing any further expansion of the tree. So what is the time complexity? Time complexity will simply be number of states multiplied by what you are doing inside each of the state, right? Now why? Because we are with this DP array, we have made sure that we will compute every state exactly once, right? So the complexity would simply be number of states multiplied by what we are doing inside each of the state. So inside each of the state, we are simply doing two function calls, that is order 1 operation. So inside each of the state, you are doing order 1 operation. Now how many states are there? Number of states would be number of unique ways in which you can call this function. So number of unique value of this IND would be n, number of unique value of this sum would be s, or rather k. So overall complexity of this entire solution is order nk, right? Which is sufficient for the given time constraint because n is 100 and k is also 100. So basically we are now able to find the power of a array in order n into k time. Okay, but if you remember, the original problem was we have to figure out the sum of power of all the subsequence of nums. So let's tackle that now. So let's say this is our nums and we have to figure out the sum of power of all the subsequence of nums. So one of the very brute force manner would be try out every possible subsequence. For each subsequence, try to figure out the power and sum them up. So for this particular array, these are various subsequences 0, 1, 2, 3, 4, 5 and then 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 1, 2, 1, 3, 1, 4, 1, 5 and similarly others. in total there will be 2 power 6, which is 64 subsequences, including the empty one. For each subsequence you will figure out the power and sum the power for everything, and you will get the answer, right? So what is the overall time complexity? Overall time complexity would be, you are doing something for all the subsequences. So if there are n elements, number of subsequences would be 2 power n. For each subsequence you are calculating the power. So we just now saw that to calculate the power you need order nk time. So overall the complexity is 2 power n into nk, which surely will not pass the given time constraint because n is up to 100. So 2 power n is something we can't afford. So we have to optimize. Obviously we will see if we have to remove 2 power n completely. That is, we can't afford iterating over all the subsequences one by one, right? So let's see what we need to do. So here comes one specific observation. So I would strongly encourage you to pause and try to see what is the computation which you are doing more than once. Okay, so notice whatever subsequences you are getting is actually a subsequence of original array, right? Now let's say you want to figure out the power of this subsequence. So power of this subsequence, to figure out that, you will again break it into further subsequence, which is 1 3 and 1 3 in this case, right? And you will see how many of these subsequences sum up to k, which will give you the power. So even this 1 3 1 3 are actually a subsequence of original array itself, right? Nothing new. So every subsequence that you are getting, if you try to figure out all the subsequence of that subsequence, all those subsequence will be part of original array's subsequence as well, right? Because a subsequence contains all possible arrangements. So if you arrange all the elements here, you will get the configurations which you already have gotten by arranging the elements of the original array itself, right? So you have 1 here, you have 3 here, you have 3 here, and you have 1 3 here as well. So that's basically one thing which we are computing again and again. So can we optimize this is something you need to think. So pause the video, try to think. So hope you thought about it. So let's reiterate the exact same thing but in a different visualization. So we have this particular array and we need to figure out the power of every subsequence of this array, right? So one of the subsequence would be the complete array itself. Another subsequence of this array would be 0 1 2 3 4. Another subsequence of this array would simply be 0 1 2 3 is. Another subsequence would be 0 1 2, and one more subsequence would be 0 and 2 as well, right? So all these are actually the subsequence of original array. Now notice inside each of these, subsequence 0 2 is common, because once you compute the power of this subsequence, you need to figure out how many subsequences of this are there which sum up to k, right? And if you try that exercise, you will end up having a subsequence which contains 0 and 2, because that is indeed one of the subsequences which sum up to k. So this same subsequence you will have here, that is, when you expand this into its subsequence to compute the power, you will have exact same subsequence 0 2 coming. Similarly, you will have the exact same subsequence when you compute the power of this particular subsequence, and so on and so forth. Basically, this 0 2 subsequence contributes more than once, because for each of these subsequences you will count 0 2 once in each of them. Why? Because when you are computing the power, you will encounter this 0, 2 subsequence that will be a valid subsequence because 0, 2 sums up to 5, right? So basically, when you are expanding, you are doing or wasting operations more than one. So this 0, 2 is something you already have in your original subsequence, and you already know that this is a good subsequence, or this is basically like the prefix of this particular subsequence would be 1, and the power of this particular subsequence would be 1. So why you are wasting the exact same operations across all of the subsequences? And that's exactly where the solution lies. So instead of expanding all the subsequences, you already know how many subsequences of the original array are there which are good, or in other words, which has a sum of k. So for each of those subsequences, you can figure out how many actual subsequence will it contribute to, right? So let's take an example. Let's say you know that 0, 2 is a good subsequence, right? Because that has sum of 5. So instead of finding out for each subsequence, let me figure out the power of every subsequence, I will say when I figure out the power, whatever subsequence I will get will also be a part of original array subsequence as well. So instead of expanding every subsequence, I already know what is a valid power, or what is a valid subsequence that will contribute to the power here. So for each such valid subsequence, I will see how many different subsequences it occurs in. Okay, so 2, 3 occurs in 1, 2, 3, 4, 5, 6, and so on and so forth. So basically, you will simply add some x to your answer for 2, 3, and you will move forward to the next subsequence. You will add some x2 for that, and you will move forward to the next subsequence. So you will add some x3 for that, and so on and so forth. So basically, for each good subsequence, you are simply figuring out how many times that good subsequence will contribute to the power of a original subsequence, right? So if you think about it, let's say you know that 0, 2 and 3 is a good subsequence. It's forming a good subsequence, that is, it has a sum of 5. So how many different subsequences are there where 2, 3 will come? That is what you want to know. So how many of them are there? It's simply 2 power 4, which is 16. Why? Because notice there are 4 empty spaces, right? So you can either decide to fill this or not fill this, that is, whichever subsequence you are taking, 0, 2 should be a part of that. There is no thinking about that, because 0, 2 is something which is a good subsequence, and you want to figure out how many subsequences are there where 0, 2 will be a part of. So 0, 2 is already a part of subsequence. You need to now know what all elements are a part of this subsequence. So in this particular case, you have this 4 spaces, so you can decide which of these elements you will want to put in the subsequence and which of these you don't want to put. So you will either put this or you will not put this. Similarly, you will either put this or not put this, and so on and so forth. So in total, you will have 16 combinations. So that is, there are 16 different subsequences which will contain 2, 3 as one of its subsequence. And because 2, 3 is a good subsequence, it will contribute 1, or it will contribute 1 power when you compute the power of that particular subsequence, right? So hope this particular point makes sense. So basically what we are saying is, I will not expand any of the subsequence afterwards, I will simply figure out how many good subsequences are there. For each good subsequence, I will see how many different subsequences this good subsequence will be a part of, and I will simply add that to my result. So let's look at this one final time. Again, the same thing, we have to figure out how many subsequent, we have to figure out the sum of power of all the subsequence of this particular array nums. So instead of figuring out the power of every subsequence, I will simply figure out how many good subsequences are there, because at the end power will, like, one, you will add 1 to the power only when the subsequence will have a sum equals to k. So let's just figure out how many good subsequences are there. So there is one good subsequence which include only 5, index 5, one good subsequence which include index 0 and 2, because 2 plus 3 would be 5. Similarly, another good subsequence which includes 0 and 3, 2 plus 3 5, 3 and 4, and 2 and 4, which all sums to 5. And finally, of length 3, 0, 1 and 4, if you take that in a subsequence, that will be a good subsequence. Now you need to figure out, let's say this one. So you need to figure out how many subsequences are there which, if you expand, will have 5 in it, or will have this subsequence which contain only 5 in it, right? And once you figure out the count of the subsequence, you will simply add that to your answer, because this subsequence will be expanded in those many subsequences, and for each of those subsequences this will contribute 1, right? So how many subsequences are there which will contain this index 5? There are total 5 indexes which you may or may not take. So you will either take this in that subsequence. So 5 will be there. Index 5 is there always in the subsequence. What all index will be there or not is something you need to figure out. So there are total 5 indexes. Each of them can either be there or may not be there. So total 2 power 5 subsequences are there which will contain index 5. And for each of these 2 power 5 subsequence, if you expand each of them, you will get 5. And 5 will be a valid subsequence, so you will add 1 as the power for each of those 2 power 5 subsequences. So basically you are adding 32 in the final power, right? Similarly, for this one, you know that you want a subsequence which have 0, 2 with other elements. So there are total 4 more elements, so each of them may or may not be present. So total 16 subsequences. Now all these 16 subsequences contain 0 and 2. So when you expand all these 16 subsequences, you will get 0 and 2 for sure as one of the subsequences, and this will be a good one, and it will contribute 1 to the power. So it will contribute 1 to the power of this, it will contribute 1 in the power of this, it will contribute 1 in the power of this, and similarly for each of the 16 subsequences it will contribute 1. So overall it is contributing 16 ones. So we will simply add 16 to our answer. In the same fashion, this will also contribute 16, this will also contribute 16, and this will also contribute 16. And finally for this, this will contribute 8 to the final answer, right? So overall your answer would be 32 plus 16 plus 16 plus 16 plus 16 plus 8 is the sum of power of all the subsequences, right? So if you have any doubts here, just rewind the past 5 to 10 minutes of the video and watch that. I am very sure you will be able to get it. Just try to sketch it out using a pen and paper as well, because this is indeed a bit tricky. Basically what we are, just to reiterate this entire thing one last time, we are saying is, what we are saying is, instead of going and figuring out for each subsequence what is the power, I will do opposite. I will say, I know that, let's say 0, 2 element 0 and 2 will form a good subsequence. So instead of expanding all of them, I will say how many subsequences are there which will have 0 and 2. And so in this particular case, let's say this is one subsequence, this is another subsequence which has 0 and 2. So what does mean is, if you expand this subsequence to figure out the power, you will get 0 comma 2 exactly once as one of its subsequence, and this will be a good one. So because this will be a good one, because of this branch, you will have plus 1 to its power. Similarly, when you expand this one, you will get 0 comma 2 exactly once, and because you already know that 0 comma 2 is a good one, this will add 1 to the power of this particular subsequence. So in similar fashion, for whichever subsequence 0 comma 2 is a part, for each of them it will add plus 1 to its power. So in total, across all the subsequences, it will add plus 1 to every subsequence in which 0 comma 2 is a part of. So what we are saying is, we will figure out how many subsequences are there in which 0 comma 2 is a part. So we found out that there are total 2 power 4, that is 16 such subsequence. So for each of these 16 such subsequence, we know that 0 comma 2 will be one of the subsequence when you expand, and because of that you will add plus 1 to the power. So overall you will add 16 plus 1s. So overall you are adding 16 because of 0 comma 2. In the same fashion, you will do the exact same thing for all the subsequence that sums to 5, because only those subsequences are there which will actually contribute to the power, right? So we simply figure out all the subsequences that can sum up to 5. For each of the subsequences, we figure out how many such subsequences are there which will contain that particular subsequence. That is, for each of these 32 subsequences, when you expand, you will have 5, and because 5 is a good one, it will contribute plus 1 to each of these 32 subsequences, and hence you will end up adding 32 in your final answer. So you will simply add them all up and you will get your final result, right? So hope the entire solution is clear. So what is the overall complexity? So what you are doing is, you are first figuring out how many good subsequences are there, right? Or rather, how many subsequences are there which can sum up to 5. But there is a catch. See, you are adding different values based on the length of the subsequence, right? So instead of knowing how many subsequences are there which can sum up to 5, you now need to know how many subsequences are there which can sum up to 5 such that the subsequence length is 1. So that, let's say you get x1 here, that is, there are x1 subsequence which is of length 1 and has sum of 5. So you will add 2 power 5 into x1 in your result, right? Similarly, let's say you get x2 here, that is, there are total x2 subsequences which sum up to 5 and has a length of 2. So you will simply add x2 multiplied by 2 power 4 to your result. So notice you add 16 for each of them, right? So you simply add 16 x2 number of times. Similarly, you will figure out how many subsequences are there which can sum up to 5 and has 3 elements. So let's say this is x3. So you will simply add x3 multiplied by 2 power 3 to your result. So overall, this will be your final result. So what you now need to know, what is the new problem? The new problem is, we have to now figure out how many subsequences are there with sum k and length l. So if k is 5 and l is 2, it means you have to figure out how many subsequences are there which can sum up to 5 and has length of 2, right? So if you have solved the original problem, the very first problem in this video, that is how many subsequences are there which can sum up to 5, this problem will you should be able to solve as well. So we are just adding one more constraint, and because of that constraint, the actual property, that is, if you just take care of the first element, the remaining problem would be a sub problem of the original problem. This will not change, and you can actually apply this exact same logic to come up with a recursion. So strongly encourage you to pause and at least try this entire thing, try to solve this particular thing by yourself. If you're not able to solve this, I would encourage you to rewind and watch the very first section of the video instead of moving forward in this particular section and looking at the solution. So hope you have tried it. So notice you have what you want is number of sequences with sum 5, length 2. So again, let's focus on the 0th element. Either you will take it or you will not take it. Only two choices. If you don't take it, what you will end up having is, give me the number of subsequences with sum of 5, length of 2 for this smaller array. This problem is exactly equals to the original problem. The original problem was, give me the number of sequences of this array with sum of 5 and length is 2. Now you are saying, give me the subsequences of this array with sum of 5 and length of 2. Exact same problem, array is smaller. Now the second choice could be, you take the first element. In that case, you are forming a subsequence and you have taken an element 2. So the entire sum of this subsequence is supposed to be 5, right? You have taken you have taken 2. Our first element is 2. So what will be the sum of the remaining elements? It would be 3, right? Similarly, the length you want to be 2. So the length of this entire subsequence should be 2. You have taken one element already. So what is the length of the remaining elements? It will be 1. So what you want is, from this array, tell me what is the number of subsequences with sum of 3 and length of 1. So again, the exact same problem, reduced array, reduced k and reduced length. So hope you can see the recursion now. So let's take a function which is answering our original question, that is, given an array and a k and a length, tell me how many subsequences are there for this array which can sum up to k and has length l. So here you have two different choices based on what you will do with the first element of the array, 0th element of the array. So you will either take it or you will not take it. If you don't take it, you will end up having the exact same array, one less array, because you have decided to drop 0th element. So whatever array it had, let's say this is this array, you will just drop this one and this entire thing will be copied here. That is, you want something for this remaining array which has sum of k and has length l. But if you take it, you again want something from the remaining array. This time the sum you want is k minus array of first element, and the length you want is l minus 1. So basically the exact sum you wanted was k, but you have taken the first element, so the remaining sum would be k minus array of 0, and the length you wanted was l. Initially you have taken one element, so the number of element that you can take now is l minus 1. You will simply figure out these values, add them up, and that will give you the value of the original function, right? So I'm not showing you the dry run for the, I'm not doing the dry run for this particular solution. If you are facing difficulty, I would strongly encourage you to watch the dry run for the previous question, wherein we discussed how to figure out the number of subsequences for array which sum up to a given number k, right? So we simply want we'll simply have one more constraint in our function, and that should be it, right? Now again, similar to the original problem, we can't afford passing the array all over to the next state, because we will face issue while memoizing it. So instead of passing the entire array, we can simply pass in an index. Why? Because we know that whatever we are doing is with the first index, so the remaining array would always be a suffix of the original array. So this index I can denote what is the start element that we are looking for, and with this I we can figure out, okay, this is the array which we are considering. So with this, the state would be updated as I plus 1 because the array is now decreased. Similarly, this will also be I plus 1, right? So this is the state transition. You can simply write the recursion and your job is done. So if you have watched this point, strongly encourage you to pause, try to find out the space and time complexity and the pseudocode for this particular solution. So the pseudocode will mostly be equivalent to what we have discussed of the previous solution. This was the pseudocode for the number of elements which has sum equals to k, sum equals to sum for a given array. So now you are saying that number of subsequences which has sum equals to sum and which contain length number of elements from the given array. So again the same thing, if sum is less than 0, you can't find out any subsequence which can have a sum less than 0 because the entire element is positive. Similarly, if length is less than 0, you can't have any subsequence which have lesser than 1 length. So you will simply return 0. And then if index is n, that is you have exhausted all the elements, that is you have decided what to do with each of the elements. So in that case, if you can only afford to make a sum of 0 and you can only afford to take no element at all. So if and only if sum is 0 and length is 0, you will return 1, otherwise you will return 0. Otherwise, this is the simple memorization thing, and this is the exact same DP state that we just discussed a while ago. So again, if you have watched this point, strongly encourage you to pause and try to code this entire thing by yourself. The time complexity would be very straightforward. What number of states multiplied by what we are doing inside each of the state. Why this? Because of this memorization. Because of memorization, we are ensuring that we are computing one state exactly once. So whenever you are asked to compute a particular state, you will either have it stored or you will compute it exactly once and have it stored, so that next time when you are asked for the same state, you will not have to compute it again. So inside each of the state, we are doing a couple of function calls and some mathematical operations. So inside each of the state, we are doing order 1 operation. So number of state is the major thing for the time complexity. Number of states would be number of unique ways in which you can call the function. So number of distinct value of index would be n, number of distinct value of sum would be k, number of distinct value of length would be n as well. So overall the complexity is order n square k, which will pass the given time constraint very easily and is an acceptable solution for this particular problem. So next we'll be looking at the code. The code is exactly what we discussed. We have this function f which takes in an index, sum and count, that is given an array starting at this particular index and ending at the last index. Return me the count of sequences which can sum up to this particular value and will only contain these amount of elements or these number of elements. So once you have this function with you, what you will do is, if you remember the exact algorithm, you want to figure out how many subsequences are there which has a sum of k and a length of 1, and for that you will multiply it with the 2 power n minus length. So that's what we have done. We simply compute the powers of 2 beforehand. After that we will go over every possible length of 1, length of 2, length of 3, length of 4, and so on and so forth. So we will figure out how many subsequences are there of length 1 which can sum up to 5, how many subsequences are there of length 2 which can sum up to 5, and so on and so forth. So we will get the value of x1, x2, x3 and x4. So this is the value of x1, let's say. So for x1 you will multiply it with the power 2 power n minus count. So basically you have taken a subsequence of length 1, so remaining array elements is n minus 1. So these elements may or may not be present in any of the subsequence. So you will simply you have 2 power n minus 1 total subsequence which will contain the chosen element. So that's what we have done, multiplied by 2 power n minus count. This will be the total number of total additions or total plus 1 that will happen because of all the subsequences of length cnt, and you'll simply add them all up and this will be your answer. So hope the entire solution makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.